My name is XinXu. I'm the SPM scientist in Birck Nanotechnology Center. I'm now giving a simple introduction to atomic force microscopy. The FM is a very powerful tool for nanoscale characterization and manipulation under various environments. How does it work? The next few slides will attempt to emphasize the important ideas without focusing on all the details. The purpose of this presentation is to emphasize the common features of most commercial FMs. Many companies make FMs, and each has different software and hardware capabilities. But almost every FM has a few things in common. In the following slides, we will review a few of these common features. How does the FM work? First, a sample is mounted to a cantilever holder, and the cantilever holder is attached to some types of scanning device. There are many ways that the sample can be scanned, but the simplest technique uses the piezo tube as shown. By applying voltages to this tube, the sample can be scanned in X, Y, and Z directions in such a way that it does not create large vibrations. Once the sample is mounted to the scanner, a micro cantilever with a sharp tip is brought close to the sample. When the tip contacts the sample, the cantilever bends upward. From simple consideration, the deflection of the cantilever is proportional to the force that the tip exerts on the sample. The first generation FMs operated in this contact mode. Then, how do we measure the cantilever deflection? There are many ways that have been tried, but the most common technique measures the reflection of a focused laser beam from the cantilever. The reflected beam is directed onto a 4-sector photodiode as shown. Each segment of this photodiode produces a voltage that is proportional to the intensity of the reflected light. Thus, each quadrant of the photodiode produces a voltage that is available for use by the experimentalist. The next slide illustrates how the four voltages can be combined to measure the normal force and the lateral force acting on the cantilever. The voltages from each sector are added and subtracted in an appropriate way to produce a slow-varying DC voltage signal that is proportional to the normal and lateral forces acting on the tip. The up and down tip motion of the normal force can be calculated by subtracting the C and D signals from the A and B signals. Similarly, the twisting motion of the cantilever caused by the lateral force can be calculated from the A plus C combination minus the B plus D combination. One common task required for careful FM works is to calibrate these voltages using no normal and lateral force. The cantilever bending is held constant by means of feedback controller that adjusts the height of the sample while the tip scans across the sample surface. In this way, the topography of the sample can be measured. There are a variety of ways to scan the tip across the sample, as shown in the next slide. In the contact mode, a nearly constant cantilever deflection is maintained by feedback loop as the FM scans across the sample surface. High scanning speed can be achieved in contact mode. However, the physical contact between the FM tip and the sample creates a significant amount of shear force that may cause damage of soft samples. The dynamic mode FM offers a significant advance for the FM experimentalist. In dynamic mode, the FM cantilever is vibrated by an external shaker. The amplitude, the phase, or the frequency shift of the cantilever oscillation can then be used to extract the information about the sample topography, as well as the as well as the surface properties like the elasticity, friction, viscosity of the sample. The lateral forces applied to the sample are reduced in dynamic mode FM, and as a result, the tip is less likely to detach weakly bonded objects from the sample surface. Dynamic FM is especially useful for imaging and spectroscopy of biological samples because of its ability to work under conditions close to their native environments. Item B and C in this slide show schematically two common scaling modes, often referred to as non-contact FM and intermittent contact FM. The fourth mode of imagery is notable because it operates off resonance of the cantilever. This mode is often called the jumping mode, and it is especially suitable for imaging soft samples in liquids. Jumping mode operation can be described as follows. At each imaging point, the cantilever is brought close to the sample and then withdrawn. Using this technique, a force versus distance curve is measured. Then the sample is moved to the next imaging point when the tip is far from the surface. Since the lateral motion occurs when the tip is not in physical contact with the sample, any shearing force is avoided. Moreover, in jumping mode, the tip-sample interaction forces can be well controlled by selecting proper cantilevers at set points. The next slide explains the basic operation required to obtain a first versus distance curve. This slide illustrates how the cantilever approaches and withdraws from a tip in a controlled way. By measuring the deflection of the cantilever, a plot of the loading force as a function of the sample displacement can be obtained as shown. Dynamic mode FM is considerably more complicated than contact mode FM. The essential idea is to vibrate the cantilever at a frequency that is very close to its natural resonance frequency. How the amplitude and the tip varies as a function of the driving frequency is shown in this slide. This plot is called a tuning curve, and it must be measured for every cantilever in order to determine the resonant frequency. Knowing this resonant frequency is very important to optimize the performance of the dynamic FM. As the sample approaches to tip, both the amplitude and phase of the tip oscillation changes in a characteristic way as shown in the middle plot in this slide. It is important to specify a set point amplitude A, which is a fraction of the free amplitude A0. The FM controller then maintains a constant set point amplitude and the tip is scanned over the sample. The basic idea behind this process is shown in the bottom panel of the slide. Okay, I can give a larger figure. By measuring the Z motion of the substrate required to maintain a constant tip sample separation, a topography map of the sample can be obtained. Okay, now we outline the experimental procedure required to operate almost any FM that you might use. Briefly, the experimentalist must first mount the cantilever appropriate for this experiment. Then align the laser on the free end of the cantilever. Center the reflected laser beam on the photodiode. Use the software to define the set point parameters. Approach the cantilever to sample. Then adjust the second parameters, such as the scan size, scan speed, scale orientation. Finally, optimize the FM controller parameters for the feedback loop. Once the operations have been carefully carried out, you will be ready to image your sample with sub-micron resolution that approaches to nanometer dimensions. The final slide in this presentation shows the pictures of two FMs presently in the Birck FM facility. One is the Asylum Research BioFM, suitable for scanning samples under liquid. and the other is the vehicle dimension 3100 FM that is suitable for imaging in ambient conditions. Thank you for your attention.